behind this talk. Actually, as you know, this conference is about beyond the obvious for weak lensing. So as I've been working for nonlinear effects and calculation of bispectra for years, I've felt like obliged to speak about that. The bad thing is that actually the progress in this field has been very slow, at least for cosmic shear surveys, and this is in surprisingly large contrast with what's happening in CMB observations and CMB data analysis, where the so-called FNL business is a very active one, both on theory and observation side. And I feel this is quite unfortunate. And one big reason is that it's probably very difficult to measure anything beyond the obvious, so in the CMB, whereas it's bound to be there in the data sets now. It's bound to be there for the cosmic shear observations. So they are next to the obvious in there. That is, there are non-zero 3-point function or non-zero bispectra in the data, and yet I think the activity in the field and the community is quite low. So this talk is to advertise measurement and theory and everything about bispectra for cosmic shear. So from the basics, that is maybe not the obvious, I hope not too obvious, to the open questions. So let's start with the basics. First of all, this is the way it is defined by a spectrum for the, let's say, the 3D density field. It could be for any scalar field, actually. And what we know from very early now results that are described in people's book is that at large scale means at linear scale, that is when the density contrast is small compared to unity, but at scales that are sub-horizon. And this is one thing which is to be contrasted with what I was mentioning before, the CMB calculations, where a lot of the action was in taking into account, so in extending this result somehow to the super-horizon regime. So, but here, except in some cases, basically we can stick with this formula. That is, we have the kernel which is known, which tells us how the modes are coupled beyond linear theory. And basically, this kernel function is a very robust function, as I will stress in a minute. So to make the connection with what I was saying, that is primordial non-Gaussianities in CMB, and basically a lot of things have been, a lot of calculation, a lot of explorations have been made for models with primordial non-Gaussianities. So in like 10 years ago, people were speaking about topological defects as a possible source, strong source of non-Gaussianities. Now people are almost exploring some models of inflation, multiple field inflation, for instance, or inflation with non-standard kinetic terms, where you would have initial non-Gaussianities in the metric field, and probably the new things for us doing now large-scale structure observation is that the primordial non-Gaussianities are encoded not for delta initially, but for the potential. So it somehow switches things, because it means that the kernel, the time-independent kernel is not written in terms of bispectrum for delta, but for bispectrum for phi. So and then the relative weight of initial non-Gaussianities and gravity-induced non-Gaussianities is scale-dependent. And this is just the k-square, which enters in the Poisson equation. We have heard about the Poisson equation for the last 30 minutes, so you will not be surprised that basically you have been kind of competing things between scales depending on the value of FNL. So if the primordial non-Gaussianities in terms of metric perturbation is large, then these things may be above unity at scales that are still sub-horizon. So this is kind of a side comment about this. The following, I would just assume that with enough of things to worry about with this function. So as I was saying, this is quite a robust kernel. It has been somewhat as a surprise in the 90s, where people explored the dependence of this kernel with cosmological parameters. that it very weakly depends on omega naught. This is just here for just a flat, I think it's a flat case. But this extends to basically any cosmological models, any content in terms of lambda or quintessence or whatever. I mean, basically this F2 is changing with the cosmological parameters to a few percent at most. This is even true when you explore models that depart from GR. So now I'm going to present naive calculations, and so you should not. So if I've understood from previous talk, this is not the correct answer, but it's an illustration, so forgive me. Right? So it's using the linear part of this theory, right? So I use just the linear and just do the calculation, and so I'm doing the beyond linear order calculation using the linear approximation for the Poisson equation, right? Not taking into account the renormalized G from small scale fluctuations. So this is the kernel that you would get, but I guess even when you are going to do it, you will start with this. This is the starting point of it. So this is a kernel for this thing extended to departure from GR, and what is to be appreciated here is that it doesn't depart very much from the value which is here, which is the standard GR result. Right? So it's not that large of a variation. And so once again, this is for delta, for the density contrast. And now, well, let's move on to one thing again. Last thing is when you go into nonlinear regime, obviously this mod coupling kernel is going to be affected by it, and it is quite dramatically. The only point I want to mention is that, but this is part of the obvious then, is that it's a quantitative change, not so much a qualitative change in the sense that F2, or what is equivalent of F2, is remaining basically of the order of unity. So in other words, where is it? So this function, so this relation between B and P is basically roughly takes roughly the same shape with this function, which is slowly or weakly changing with time. So now, basically, this is a state of, this is an understanding of the density field, and now it has to be translated into statistical properties for the cosmic shear observations. Right? So let's start with a simple object, a simple way of thinking of cosmic shear observation, which is to consider the convergence field. As you know, the observations are actually not giving you kappa, this convergence field, but rather the shear field, that is a deformation field. But they are related. So in principle, from a purely mathematical point of view, and I'll come back to that, shear and kappa are just the same, right? So now, in principle, everything all the statistical properties of your field are encoded in those of kappa. So the relation between kappa and the density contrast is this one, because this is just an integration over the line of sight with kind of weight function, which depends on the cosmological parameters. There's not much to say, so that it's simple, quite simple to go from there to there in terms of cosmological, in terms of statistical properties, and you can compute the variance and the skewness, which is basically the amplitude of the three-point function in a reduced way, but is equilateral, depending on the language, equilateral triangle configuration, basically. The interesting thing, which was pointed now more than 10 years ago, was that because of this weight function, which depends on the cosmological parameters, you can actually break the sigma 8 omega naught dependence on the variance while considering this ratio, which was not true for the density field. So one first important difference between density contrast, that is when you measured in galaxy catalogs and cosmic shear, is that when you go to higher order moments, then you are sensitive to your cosmological background, to cosmological parameters, omega naught. And this is because basically kappa is not delta 2D because it's not normalized. You do not divide by the average of this weight function. It's unnormalized density contrast. And because of that, it's still sensitive to the cosmological parameters. So this is basically one big motivation to actually going after three-point function of bispectra, is because it's sensitive to other things than just sigma 8. And now, just to finish this thing about departure from GR, actually, for a similar reason, kappa is also sensitive to departure from GR. It's because kappa is not, once again, it's not density contrast, it's actually Laplacian phi, unnormalized Laplacian phi, and Laplacian, and so this is the left-hand side of the Poisson equation, not the right-hand side. And if you change the Poisson equation, then you change the statistical properties of your field. And this function F2, which was for the density field here, which was weakly dependent on departure from GR, the one that you compute for Laplacian phi is depending on departure from GR. So these are the good reasons to try to measure the three-point function of the convergence field. Now, let's go back. I mean, let's really think of how to actually do the measurements. And as you know, as I was mentioning, kappa is not what is measured. What's measured is the two-component shear field, which is a spin to fields. And mathematically, out of that can be two scalar quantities, one real scalar, one pseudo-scalar quantities, so-called E and B fields. This is quite known, but I'm just saying. And this is basically, and to be a bit more specific, because of this Laplacian, you know that you are not going to measure kappa at a given location, whatever the precision of your measurements. You measure kappa to the kappa when the large-scale modes are filtered out. And to say it in the words, when you filter out the large-scale modes, you're basically measuring what is called MAP, so the aperture mass, which is basically kappa filtered with a compensated filter, that is with a filter which in K space has a band that is has a low K and high K cut. So, and you can do the same for B, right? The same filtered field, and basically at the end, what you actually have to consider is are the statistical properties of these two fields, and not the one of kappa. Or rather, actually, it's a statistical. Anyway, so you can do the same exercise, that is compute S3 not for kappa, but for this map field. This was done also 10 years ago, a bit more. And so we know what to expect. And then now, how much time do I have? From now on, basically there are, I think, two paths, two ways. Either you think that observers and people who do data analysis are good enough to produce reliable maps, aperture maps, and so you can directly measure higher order correlation function in those maps and compare to the theoretical predictions. But just one step back, two steps back. You know that to have the value of the map at a given location, you have to integrate, over a circle with a given profile, and so this is the radial part of the shear field. So you have to have the data available there at each point. And in practice, you have a lot of holes, of masks in your maps, in your shear maps. So this is not always, you have to basically extrapolate most of the time. But I'm not doing that analysis myself, so I don't want to comment too much on that. So the only other, from a theoretical point of view, it's always a bit worried when you have to extrapolate things in between within the hole. So you may want to take a safer path and basically not to compute things at the map level, but at the shear field level. That is, as I will just say in a minute, basically when you compute the power spectrum or the two-point correlation function, it's much easier to do it at the shear field, because you take, once you have two galaxies in your catalog, you just bin them in distances, measure use the shear at two different galaxies, and it gives you one contribution to the shear two-point correlation function, given distance. Also, two components of the shear correlation function, and you don't have really to reconstruct the maps to get to its correlation function. Just one flash. Well, if you use fast one, it is trusting data reconstruction, then you can actually show that you have a non-zero skewness in the already old surveys. So it's there. Yeah, so what I was saying about the two-point function is that there are a lot of symmetries and a lot of non-trivial properties associated with the shear field. Obviously, one is related to the just fact that it's a spin-2 quantity, so that it does some properties when you change the coordinate system. And the other thing is that you expect no B modes. So basically, this can be used either as a test of your analysis or as a features from which you can use, which means that actually when you measure correlation function of the shear field, you have more information than you need to actually recover the one which is cosmologically significant. To say it in other words, if you have 2 points, you can define two types of correlation function in the shear field. The one which relates the two components of the shear along this axis, the psi plus, and the one which relates the two other components related to the other axis, the psi cross. The psi plus, the cross correlation being zero from symmetry reasons, but these two have no reason to vanish. They have no reason to vanish, but at the same time there is a relation between them, and this is illustrated here, is that if you have no B modes, then you expect the cross correlation between the shear there and the B mode there to vanish. So, and now if you remember how I can calculate B modes is by integrating one component of the shear around this point B, you can actually show that if you do that, basically you are integrating psi of this. I mean, you have a point running here, so psi plus and psi cross, two components of that, with, I mean, properly projected, and you integrate that, and you do an expansion with respect to this radius compared to that distance, and you get that this, if this is to vanish, then you have a relation between these two components of the correlation function. So this is just another way of stating what Clayton and collaborators have done in the early in 2002, writing relation between psi plus and psi cross, and you can actually do more. That is, you can relate psi of the kappa to these two components. So basically, this is what we would like to do for the three-point function of the shear field, to extend that. But then, well, let's try. First problem is that when you have 2 points, you have an obvious choice of coordinate system. Right? The line that joined the two was one obvious choice for your axis. When you have 3, you're stuck because you don't know which one to choose. So you have, basically, you can choose one side of the triangle, or you can just take one point in well, here it's, I guess it's the barycenter of this. I'm not sure actually. Is it the barycenter of this triangle, from which you use as a way to define the basis for each shear for each summit of the triangle. So this is one choice, but then the absence of B mode, if I do the same trick, integrate over for a circle, you see that it's going to mix both scale dependence and angular dependence of my 3-point function. So it's a complicated, even more complicated functional of this, all this 3-point function, and it's not easy at all to implement a way to deproject things, right? To project B out, if you want. So this is one difficulty, and now basically the results are very sparse in terms of what to expect for the 3-point function of the shear field, and probably this is one reason from a theoretical point of view we've not been very far. It's that even with simple model, you've got very complicated dependence for this 3-point function. This is an illustration here from the halo model, where you just assume that the density field is obtained. Statistical properties of density field can be obtained with a collection of halos. So this is the work by Matthias and Roman in 2003, where they computed different components and modes. You can see all this shear field with the definition I was given before. And this is the what's called one halo contribution that is 3 points assumed to be the same halo. So, but even though the halo was simple, you have to do it numerically. I'm going now to advertise one piece of analytic calculations I've done a few years ago, which this paper apparently was totally unnoticed, so I'm going to advertise it. Sorry?
Because your equations are too small.
Yeah. I'll zoom. I'll zoom in a moment. So this is the simplest model I could think of to do the explicit calculation of the 3-point function of the shear components. And this is a power law halo model. That is just a halo with a power law its density field, and calculate the one halo contribution for the 3-point function. So 3 points given geometry, and the halo is at random position, right? And thanks actually to Roman's insights into the math of that, it's possible to do the explicit calculation of any correlation function you want. That is, for instance, the 3-point kappa correlation function, or the 3-point shear correlation function. So this is one of it here. So something I didn't say, that from a symmetry, just a symmetry aspect of the shear, you have different components. If you think of the shear fields as a complex number, right, gamma 1 plus I gamma 2, then you build spin 2 or spin 6 objects, right? Spin 2 if you have gamma times gamma bar, the complex conjugate. So this is exactly, if I were computing the 2-point function, which would be this kappa kappa, right, the same scalar quantity. But now for the 3-point function, this quantity gamma gamma bar gamma is a spin 2 quantity, which is like a shear field. So I can draw actually this shear field. This is what I was showing here. So I'll show you the expression afterwards. So this is the peaks here are representing the orientation of the shear field, and the length, the amplitude of the shear field. And you see that the amplitude of this 3-point function is as a penny shape, which is much more complicated in terms of structure than just what I was started from. That is just halo with a simple profile, and this is where the challenge is. That is, it's a complicated angular dependence that you want to use in practice to actually do measurements, and this also. So this is for different profiles. They share some similarities, but as you have a kind of strong edge in between, and this zero location there and extension there. These are obviously not exactly similar, so this is to be understood probably. And I was showing this the awful part of it is that even though I started with a simple profile, power law, one number, I end up with this. So this is alpha, Z number, right? And you don't even see the whole complexity of it, because you don't know what is G, big G, G1, and H, which are hypergeometric functions of some type. So it's complicated, and this is why I stopped actually, because the goal would have been to somehow find the optimal weight of these different functions, that is to invert somehow this amplitude to get back to a good way to measure the amplitude of the three-point function. So this, nonetheless, we tried. Actually, it was a bit before with Yannick and Ludovic van Verbeek. We tried to do an actual measurement of this three-point function. So I was showing that the theory, from a theory point of view, you expect this kind of funny elongated shape. This is something we had observed before in a numerical simulation. So this is basically the same quantity, right? Gamma bar times gamma, so it's a spin two fields. And this is location of x1 and x2. And you see this pattern here. So in between these two, you have kind of regular pattern here. And this is what we used. So let me be a bit more explicit. What we use to measure the amplitude of the three-point function, that is, we average this quantity in this region, just because there the signal appears to be regular and basically uniform. So you take this uniform region, average out, and so you've collected all the information in one number. It's certainly not the optimal way of doing it, but it's one way, which doesn't rely on the reconstruction of the map field. So you just take, each time you have in your catalog you have triplets of galaxies, you compute this products and put it in a bin, right? And so you have only one scale, one dependent, which is a scale, which is the distance between these 2 points. Yes?
What is the advantage of this quantity versus, for example, the skewness of the aperture mass?
Well, the problem with the aperture mass is that, as I was saying, when you compute the aperture mass at a given point, you have to be sure that you have galaxies all around, that it's properly calculated. If you have a mask within, close to where you compute the aperture mass, then you're actually applying a different effective filter. Right. So this is so at the end, I guess it doesn't make much difference. That is, if you have to do it in an effective way, you just take a numerical simulation, mask it, compute your quantity, and compare with what you've seen in the real world, and okay, this is fine. But if you have to have some theoretical insights in it, I think at some point you have to have a better control of what you're doing. And this is my claim here, is that if you go to shear correlation function, you have a better control of what you're doing. Maybe we can discuss it.
But you can calculate the skewness of the aperture mass from the three-point correlation function.
Sure.
You don't care about the mass.
You can calculate. No. But the problem is the skewness of your aperture mass in your actual catalog is the aperture mass is something complicated because of the masks. The actual one that you get, right? You don't agree?
Yeah, but you don't care about the actual aperture mass map.
Why do I don't care? At the end, I care, no?
No, you calculate, you take the three-point correlation function and then integrate to get the skewness of the aperture mass.
Yes.
This is also an integrated quantity. So then the skewness of the aperture mass is also quite directly obtained.
So this is the last step I'm not sure I'm going to buy. From the data, you don't have the aperture mass. You have something which is reconstructed aperture mass.
I don't think that this quantity is influenced by mass. The shear correlation function doesn't depend on mass.
Depends on which scale. If you want to see that at large enough scale, well, maybe I should have said in the beginning, if you want to be able to measure the amplitude of the three-point function in a quasi-linear regime at, say, one few megaparsec scale, so you need to have aperture mass at that scale. But you are bound to have masks. Maybe yes.
So in my asked the CMD people how to calculate the three-point function or my spectrum of say, the polarization. They would do some C inverse weighting thing and multiply by bispectrum template and give me the amplitude, or maybe give me several amplitudes by several templates. Why is something analogous to that not the best approach for reclosing?
Yeah, this is a good remark.
This is what we did in that paper with Karim.
This is what you did.
Yeah. So we had a template. The problem is the template is not robust. You have to assume something like a Halo model or something.
Yeah, that's a problem. Yeah.
So we don't have a good template, I would argue. Huh?
To get the weighting right.
Yeah.
Well, you take the template you expect,
Yeah.
and the derivative of the template with respect to each of the cosmological parameters you're trying to measure, and why does this not give you all of the information?
No, but I'm
We
sure.
don't have a template.
I'm not sure I understand it.
If it's not the right template, it's unoptimal.
Yeah, yeah.
It's
Yeah,
still-
what we show is that, okay, it looks reasonable, but it has to be done better. We did very crappy simulations.
No, the only point, yeah. So probably the message here is that we know too little of these things to be able to infer what's the best strategy at the end. And there's probably my message here.
You're saying you don't know how to predict the bispectrum from cosmological parameters?
No,
Or
no. For the shear field, how to go from. This is what you were saying, Roman. That basically you've done this exercise for the Halo models, right,
Yeah.
with Karim,
Right.
and so, well, if. So this is one example. This is one example of analytic calculation, and basically that's it, right? I'm not aware of many other work. So for the shear field, at the shear field level, very little is known. And now you may say, as was said, why do you care about that? Just take map reconstruction and do this at the level of the mass of the aperture mass. But I'm not so. I'm uneasy about that. And because of this mask problem. So to say it in other words, the map field is just a collection of modes in Fourier space, right? So just collect mode in some way. But the noise properties of these modes are complicated and much more than, because of the masks, much more than in CMB, I guess.
well, in the CFD we have masks as well, and
What?
the condition ratios of various matrices are usually much larger than with lensing, where a lot of what you are doing is close to the noise dominated regime. So I'm not sure.
Maybe this is something to discuss. Maybe there's no.
This is too much harder.
I don't know. I'm not familiar with CMB and not so much. Yeah, so I'm going to go. So this is this is exercise was done in a few years ago, and we've been able to actually give the first detection of a non-Gaussian signal in this early survey, which was compared. And so going back to what the discussion was at the beginning, that this ratio of the 3.2 square of a second is omega dependent. We've been able to show that indeed, even with very small surveys, which was about 8 square degrees, I think, the error bars were comparable to what you expect as differences between different major cosmological models. But I guess now we are not discussing this kind of models anymore. And then to make the connection with previous talk, this is now same plot but with modified GR in a wrongly calculated way, but still. So, just to conclude now, I think too late. So I think one good reason to look for that is that it is there, and we know it is there, and we should spend time trying to measure and understand it. And as I was saying, it's a test of many fundamental things from, actually, just to start with, this mod coupling, this F2 function is just a signature of the gravitational instability paradigm, and at some point has to be tested just as a consistency check for the theory. And a signed result will be constrained on departure from GR. And also it can be used to constrain cosmological parameters, so it's not yet clear, I guess, how much you gain if you, in terms of precision, from 2-point to 3-point function. And probably something, but maybe not that much. But there are many problems to solve, I guess. I think a better understanding of bispectra in general, even at the matter level. I mean, at the fundamental level, we're far from having a fully predictive, theory at the precision you want to have it. So there are many approaches. I'll just list them. So there's one thing which has not been discussed in the community for cosmic shear, which has been discussed a lot in the CMB community, is different configuration may tackle different problems. This is clear from the CMB physics point of view because so-called squeezed limit, that is when you compare, so it's a triangular configuration when you have small scale versus one large scale. And basically, in the context of CMB physics, it means that the large scale is super Horizon and the small scale is super Horizon, and you're basically testing something about the mod couplings or the origin of mod couplings. Here, I guess it's always easier to do measurement in the equilateral version because all scales are smaller and the signal is larger. But you may argue that it might be interesting to go in the squeeze limit. Maybe one way would be to meet the other regimes that is due to mod couplings in the primordial metric field. And also maybe the theory is easier. I don't know. So I leave that for you. Thank you.
All right.
Any more questions for Francis?
No? Well, one question. So you assume for the map, for the shear statistics, there's always 0 B modes, right? But what happens if you have some contamination? What happens in your statistics? How does it propagate to your estimator?
It's a good question. I don't know. So there's one extra function you may at 3-point level, which is EBB, right? There's only one more. EBB are 0 for variety reasons, and so is BBB. So you may have non-zero EBB. What does it mean? I don't know, because in terms of for the map statistics, it's just that there is non-zero map, it's a combination. For the shear field, if this is complicated scale dependence hidden there. No.
But you could also imagine with a non-zero B that one of your EE estimators becomes biased.
What do you mean? That you've
Shown, well, you make the assumption that B has to, when you define the statistic, you make the assumption that B has to be 0. But in you might, when you signal it, right?
Yes, that's right. That is when we measured this in the Descartes survey.
Right.
We may have made a mistake. Indeed, we may have included spurious B modes that would help build up this signal. So we made the assumption that the 3-point function was free of B modes, and just correct for the amplitude of the 2-point function when we did the ratio. But also when you deal with E and B modes, you have to worry about the finite size effect and so on. So again, this is a complicated thing.
One last question. All right, so let's thanks Francis.